Hi everyone, this is Miki Bonacci from the Physics Department of the University of Modena and Reggio Emilia and from Siena Nano in Modena. And here I want to present the Yambo plugin for the AiiDA infrastructure. I'm a current developer of the plugin together with Nicola Spallanzani from Siena Nano in Modena. And we had also as developers Antimo Marrazzo, Gianluca Prandini and Michael Latambo. Yambo is a many-body perturbation theory code within you can compute electronic and optical properties of a material. Suppose to have studied a system with density functional theory, DFT, and so to have obtained the ground state structure. Then suppose you want now to have a correct picture of the electronic properties by taking into account many-body effects like screening. Yambo is the right tool to do that. Indeed, starting from DFT results, for example, with Yambo it is possible to compute the electronic band structure using the so-called GW approximation. Then, the absorption and the electron energy loss spectra can be obtained by solving the Bethe-Salpeter equation that takes into account the electron-hole interaction. There are other approximations and methods implemented in Yambo, like time-dependent DFT, and the electron phonon treatment. And if you want to know all the Yambo features, you can go to the official Yambo website, third listed below. A typical Yambo flow is the following. You start from a DFT result, computed for example with quantum espresso or a binit, and then you have to use the P2Y executable to convert these results in a Yambo readable format, and then you are ready to run the GW or Bethe-Salpeter calculation with the Yambo executable. Then you can do a final post-processing with the YPP executable. Now let's have a look at the plugin and how it works. The main actor of the plugin is the YamboCalculation, that is an AiiDA calc job that directly interfaces with the calculation. It uses the P2Y and Yambo executables and requires as a parent calculation a quantum espresso one that had to be done using the relative AiiDA quantum espresso plugin. Inputs are managed within the Yambo calculation as many other AiiDA plugins show, so the input parameters have to be prepared as a Python dictionary, then converted to the AiiDA dictionary format and stored in the AiiDA database. After the run, there is a parser that stores in the database all the useful outcomes of the run and understands if the calculation was successful or not. The calculations that can be run with the plugin are all the possible ones that you can do with the Yambo executable, starting from the independent particle random phase approximation RPA to GW and Bethe-Salpeter. The last one, the Bethe-Salpeter, will be available only from the version 2 that will be soon released. It happens that a calculation fails, and if you want an efficient and automatic error handling, you have to implement a work chain that lies on the top of the bare plugin and takes care of a restarting system. In the Yambo AiiDA plugin, this is represented by the lowest level work chain called Yambo Restart. This work chain takes care of several error handling methods and try to restart the failed calculation. We go from the classic time exhaustion error to the more complex and tricky parallelism and memory errors. Indeed, as a GW calculation have a huge memory usage, you have to set in an efficient way the parallelism options available in the Yambo code. So, this work chain implements an automatic parallelism generator that is used in these cases. The next level work chain is the so-called YamboWorkflow, which takes care of all the necessary steps to run a GW result. So, starting from the DFT calculations within the PW-based work chain of the AiiDA Quantum Espresso plugin, to the GW calculation through the Yambo Restart work chain. This means that providing all the inputs, you can calculate from scratch, starting from the FT to towards the GW proper calculation. And as both Quantum Express and Yambo uses the restart word chains, here the error handling is automatically ensured. Then the top level word chain in the plugin is the so-called YamboConvergence. This performs the convergence of the quasi-particle correction with respect to critical parameters used in the code. This is a fundamental task in a GW calculation, as with respect to the FT, here we have a lot of parameters involved that can be also interdependent, so it is mandatory to converge in a proper way them in order to have a correct result on the quasi-particle correction. The goal of this word chain is to automatize the process of convergence over a given number of parameters that usually require a lot of time to be done manually. Examples of the involved parameters in Yambo are the plane wave cutoff and the number of empty states used in the calculation of the self-energy and the screening matrix. First input that you can provide to the word chain is the quantity that you want to converge. That can be a gap or a single quasi-particle level of your system. Then you can provide the convergence path for an arbitrary number of parameters and the relative convergence threshold and other convergence informations. You can find out how to set in a proper way these inputs by reading the dedicated web page on Read the Docs. Here we have a plot of what you can expect as a result of this word chain. The workflow performed about 40 calculations, so 40 steps, changing each time a given parameter or a group of them that you can distinguish with different colors. And at the end we have more or less convergence. This example is relative to the two-dimensional HBN, and for more or less convergence I mean that here we have not pushed further the convergence on the k-point mesh because this was just a test. The convergence can be pushed further by increasing the convergence threshold. We can observe from the first part of the plot that we have an interdependence between the empty states in orange and the plane wave cutoff for the screening matrix in green. As when we change one of the two, the other is no more converged, so we have to recompute the convergence over the second parameter. And this is the main task when we do GW convergence. By iterating multiple times on these two parameters, we observe an overcome of their interdependence by a flattening of the convergence curve. Okay, now some example of the usage of the plugin for scientific production. The first work that I want to briefly show is the one of Antimo Marrazzo. It was a developer of the plugin and co-workers from the PFL in Lausanne. They made a screening on a set of more or less 2000 materials to find novel quantum spin Hall insulator. To do that, they first did a screening on the base of the FT calculations, and then they did a final GW refinement using the Yambo plugin. They successfully identified 13 monolayers that are candidates for quantum spin Hall insulator. And these materials can be promising for many technological applications in the field of electronics, spintronics, and topological quantum computing. Second work that I want to mention is the one of Mike Tambo and co-workers, mainly from CNR Nano Modena, about the study of the electronic and optical properties of doped titanium dioxide. two studied cases are the hydrogen and niobium doping of titanium dioxide, and the final result was the calculation of the optical spectra of pristine and doped titanium dioxide, and a characterization of new defected energy levels that appear in the band gap region of the modified systems. These helped to explain the enhancing of the titanium dioxide absorption of solar energy. It is a leading topic in fields like photocatalysis and solar cells. It is important to underline that these two works were performed using a preliminary version of the plugin without using the automatic convergence workflow that I shown before, but paved the way to build the workflow as it is now. Now let's see a test that we have done with this automatic convergence workflow. Let's see a test done on GPU accelerated architectures. Indeed, the recent porting of the Yambo Code on GPUs allowed us to test a so-called GPU accelerated Yambo convergence. Here we tested the convergence for the bulk titanium dioxide on the P-state supercomputer, and the plot shows the convergence of the gap with respect to the number of steps, number of iterations of our workflow, and we can see that after 28 steps we have reached convergence of the band gap at the gamma point. As you can see from the table, the human time, that is barely the effective time that we had to wait to have converged an accurate result from this workflow, is more or less a day. All of that without human supervision. So, combining AiiDA and the Yambo plugin with the GPU accelerated architectures, it is possible to perform high throughput studies in very short time. So, high throughput GW made real. Then, if you're interested in computing many body properties of a material with the Yambo plugin, you can install the plugin from pip or by cloning it from the GitHub repository. And then you can have a look at the plugin documentation on Read the Docs, in which there are some tutorials to run plugin and the word chains that are provided. If you need support or if you have some question or observation about the plugin, feel free to contact us, in particular me and Nicola Spallanzani. And thank you for the attention.